So far we have discussed polynomial interpolation that connects n plus 1 points xi, yi in two ways. The first way is via inversion of Vandermonde matrix, and the second is to use Newton's approximating polynomial. When we interpolate using a polynomial, essentially what we do is the calculation of this ai, which are the coefficients of the polynomial. We have seen that as we go from this Vandermonde type technique to Newton's technique, the calculation of these coefficients become easier. Now we want to stretch ourselves and we want to go further such that the calculation of these coefficients are not at all necessary. In fact, if the calculation of this coefficient comes down to just getting this f of xi, then we can say that f of xi are already known because they are same as the yi, so the coefficient calculation is not at all necessary. How can we achieve that? Let's see by discussing the Lagrange interpolating polynomial. So let us think about what we have done so far. We have used a polynomial such as y equals a0 plus a1x plus a2x square up to an x to the power n. And then we have used Newton's polynomial, where we have used y equals b0 plus b1x minus x0, b2 x minus x0 into x minus x1, etc. Now if you look into it, you will see that the standard polynomial, that is a0 plus a1x, etc., I can write it as a sum of ai psi I of x. And here you can think about that we are representing this function y equals fx as a linear combination of a set of basis functions, and these basis functions are psi I of x. In this particular case, the basis functions are 1, x, x square, x cube, all the way up to x to the power n. Similarly, if I go for Newton's polynomial, I can write this expression of Newton interpolating polynomial as a sum of bi phi I of x. That means here also we are having a linear combination of the basis functions, and the basis functions here are phi naught equals 1, phi 1 equals x minus x naught, and all the way up to phi n, that is the product of x minus xi, where I goes from 0 to n minus 1. So the idea is that as we leave the technique of inverting Vandermonde matrix and we use interpolating polynomial, what we are doing is that we are selecting good quality basis functions. They are good because they help us to get the coefficients easily. So the goal is to select basis function to get the coefficient easily, and we want to stretch this to an extent where we don't want to calculate the basis coefficients at all. So we want to design the basis function in an intelligent way, so the coefficient calculation will render unnecessary. And let's see how we can do so. We do so using certain type of interpolating polynomial known as Lagrange polynomial. In Lagrange polynomial, the basis functions are L0 of x, L1 of x, Ln of x, etc. And the coefficients are f of x0, f of x1, etc. all the way up to f of xn, which means that we already know this f of x0, f of x1. They are part of the data set given to us, which means that we don't have to calculate the coefficients at all, but we have to figure out what are these basis functions. Once again, here the basis functions are Li of x for I going from 0 to n, and the coefficients are f of xi, which are known. So now we have to know this basis function L0x, L1x up to ln x, where the coefficients are known. And the next part we will see that how we exactly get this Lagrange basis functions L0, L1, etc. Each of these basis function, if you look into it, they are essentially a polynomial. This is true for even for the Newton's polynomial, or even before that, if I take 1x, x square as the basis function, they are also polynomials. So each of these basis function is a polynomial, and their degree cannot be greater than n. Either they are up to n or they will be less than n. That is true for all sorts of interpolation, not only Lagrange. Now let's say that we select certain arbitrary x, that is xk. It could be one of these points xi, yi, but it is not necessary. It could be anything. So in this one of this x equals xk, some arbitrary value of x, and if I write that in terms of Lagrange polynomial, if Lagrange polynomial passes through this point, then for x equals xk, the value of this function will be L0 xk f x0, L1 xk f x1, etc., etc., ln xk f of xn. Please note that the f are fixed here. They don't depend on xk at all. F of x0, f of x1, etc., these coefficients are known previously. As soon as we know this data set xi, yi, we know this coefficient. F x0 is y0, f x1 is y1, etc. So they are known. And we can write this as Cik f of xi, where this Cik I write as Li of xk. This is just a symbol and it has no other inherent complexity, at least up to now. So you can see that at a given point x equal to xk, the value of f, what we are getting f at x equal to xk, is essentially a linear combination of the different f of x0, x1, etc., etc., which we have received from the given data. So at any point, if we want to find the value of fx, what we have to do, we have to take a linear combination of this initial f of x, and this linear combination will be combined based on the value of L at that xk. This f of x0, x1, xn, etc., they are of course independent coefficient. For instance, the value of f of x0 does not depend on value of f of x1. They are independently, we have received these values. They may be coming from certain experiments that we don't know. We don't have to know, but we know that they are constant and they are independent of each other. They are only the input to find the value of fx at certain arbitrary point x equals xk. And until now, whatever we have discussed, this idea is applicable to all interpolation routines, not necessarily only Lagrange's interpolation. Now we move forward. We have this x equals xk, and we know that at x equals xk we have Cik f of xi, and these xi's are the measured point here which we have received as a data set, probably coming from measurement, probably coming from other sources. We don't have to know. Now let us do some small tricks. What we do is that we will pick up these points xi, yi one by one, and we will put it in this expression that f of x equals xk is Cik fxi, and let's see what happens. So f at xy will be C0 I f x0, C1 I f x1, all the way up to Cn I f xn. These c's are coming from here, and these xi's are the actual points where we already know the values. So we want to repeat this for all i's going from 0 to n. So what happens exactly if let's say we take a case I equals 0, and we know that here xi equals x naught, which means that in place of xi I put x naught. This will be c00 f x naught, c10 f x1, etc., up to cn0 f xn. Now we know that f x naught is known, and it is completely independent of fx1, fx2, etc., up to fxn, which means that in this particular expression the value of fx naught does not depend on fx1 at all or fx2 at all. That means that c10, c20, etc., it must be 0, and c00 here, that should be 1. Similarly, we can test for I equals 1, that means xi equals x1, and once again I write this expression, that is f of x1 equals c01 fx0 c11 fx1, etc., up to cn1 fxn. And if I use the same argument as before, that fx1 does not depend on fx0 or fx2 or any other f for that matter, then c01, c21 up to cn1 all will be 0, only c11 will be 1. Now we can generalize this, and we can write that cij, which is li of xj, will be 1 for I equals j, and cij, that is li of xj, will be 0 for I not equal to j. This is very important now, and we have to work on this for some time. So now let us concentrate on this, that li x equal to xj equals 1 for I equal to j, li x equal to xj for 0 for I not equal to j. What does that mean? It means that if I take any of these L functions, for instance, let's say this is L0x. How does this function look like? This is one of these basis function. This basis function will have zeros for x1, x2, x3, etc. And at x0, this basis function will be 1. And it has zeros everywhere for all other points. Please note that this x0, x1, x2 all the way up to xn, these are the points we have received. These are our given data set. And our basis function L0 is such that it will have 1 at x0 and it will have 0 in all other x's. Similarly, for instance, if we have L1x, then it will have 1 at x1 and it will have zeros at all other x's such as x0, x2, etc., all the way up to xn. If this is the nature of this basis function, how can I write that? So these basis functions have their roots. For instance, L0x has its root at x1, x2, x3, etc. So for any function Lix, it has the roots of j equals 0 to n and j not equals I. So we'll only drop that I for which this Lix at that particular I point it will have one value, but it has roots. Other xi's will be the root of this function. That means the general expression of this Lix will be something multiplied to the product of x minus xj, where j is not equal to I. Just to understand this process here, you can write this L0x equal to some arbitrary alpha naught multiplied by x minus x1, x minus x2, etc., up to x minus xn. This alpha naught, of course, we have to figure it out. We don't know yet. How this is coming? Because x1, x2, etc. root of this L naught x, I can write L naught x in this manner. And also, I want to emphasize here that L naught x does not have any other roots. These are the only roots it may have, because if I multiply all these first brackets, I get x to the power n, and I know that all of these basis function cannot be, their degree of that polynomial cannot be greater than n. So these are the only roots that L naught x will have. So now we have arrived at certain expression of the basis function. Only thing that we need is to find out the alpha I. Now you see that this expression of this basis function Li, we have got it using this concept that Li at x equal to xj equals 0 for I not equals j, and that gives us the roots of Li, and that gives us the expression of Li like this. We don't know the alpha yet, but we know that Li at x equal to xj will be 1 for I equals j. So if I use this expression, I'll get an expression for alpha I. So let us see. This is alpha I, and in place of x, if I write xi, then alpha I and a product of xi minus xj will give me 1. Of course, j cannot be equal to I. And this means that alpha I equals 1 by product of xi minus xj. And thus, Li of x is a product of x minus xj divided by xi minus xj. This xi minus xj is coming from this alpha I, and these are the expression of all our basis function. We have reached the basis functions finally, and the function polynomial can be written now as y equal to sum of Lix fxi, and I know what the Li's are, so we are all set. And this form of interpolating polynomial is known as Lagrange interpolating polynomial. The coefficients in Lagrange interpolating polynomial are fxi. They are known from the input data set, so we don't have to calculate them, but we can immediately see that the basis functions are not very easy to get, so we have to put some effort in finding the basis function. But if we do so, then the next part is easy because we don't have to calculate the coefficients. For your exercise, you take up a function y equals to ln of x, and then you approximate this function as a polynomial of degree 2 in the interval 1 to 6. First you do it with Lagrange interpolating polynomial, and then you can repeat the exercise using Newton's polynomial. That's all for this lecture. Thank you, and I'll see you in next class.